Yes. Okay. So this is the LCS4 document that is there, and so your comments or queries on this one.
Could you please explain the mathematics of the oil gauge one?
Of the
I don't know what it's called, oil gauge or something, fluid something, ma'am.
Hydraulic
What?
actuator.
which page?
Yes, ma'am. Third page, ma'am.
Hydraulic actuator. Yeah.
Yes,
So
ma'am.
And also the D-thread signal, ma'am.
yeah, so in this one, dither signal. Okay, dither, I got that point, and Shuddha Shuddha, I still didn't get your point. What are you?
Ma'am, the mathematics, ma'am, ma'am, after the construction, you explained the mathematics, ma'am. I didn't really get what was happening there.
Oh, okay, fine. Now, what happens is, wait, let me see one out. Yeah. So in this one, what happens is that you've got this hydraulic actuator, and let me put it on the hand. Yeah. So this is actually the driving element, the pilot valve. Okay. And this is the power piston which is moved using that. Okay. So a small displacement in this can be used to drive a much larger mass. Power piston means movement of a power piston. That means you're driving a larger mass. Okay. But you don't want your control signal to be too large. If you have to apply, say you want to move a car, so pushing a car, manual labor, so the amount of push needed to push that car, that would be, manual labor would be very large. You don't want to do that. Instead of that, what do you want to do? You want to be able to mechanize it or something so that you give a sort of the engine thrust to that system and the whole system moves. Okay, so something like that. So here is the same hydraulic system itself. So this is the pilot valve which is moved. So this can be driven by the control system, the movement of this one, and that decides as to how much this power piston will be moving. Okay, is this okay?
Yes, ma'am.
Now, so then what happens is, I think in the presentation you understood that when you are shifting here, oil is coming in here and so on and so forth. That part must be okay.
Yes, ma'am. Yes, ma'am.
Yeah. So now the point is, so this liquid mass flow rate, so everything is driven by this oil flow into port 1 and the oil drain out of port 2. Okay. Yes, no, please.
Yes, ma'am. Yes, ma'am.
Yeah. So that means our concern is essentially this oil mass flow rate. So this decides as to how much it will move. This power piston will move. So this oil mass flow rate, what all does it depend on? Naturally, it depends on this initial movement that is given to this pilot valve, X. Right?
Yes, ma'am.
Yes, ma'am.
And what else? It also depends on whatever is the pressure differential between these two ports, P1 minus P2. Okay, so this P1 minus P2 is denoted as this delta P. So these are the two factors. One is how much is this one moved and what is the pressure differential between these two. If there is no pressure differential, then the amount of force needed will be different to if there is a positive force pressure differential versus if there is a negative pressure differential. If there is a negative pressure differential, you have to work against it, get it to zero and then get this to a positive pressure differential so this moves. Right?
Yes, ma'am.
Okay. So hence, it's a function of this as well as this. Now, so from the physics of it, you understand that you can think of Q as a function of X as well as delta P. Now, since that is so, interpreting it into a mathematical part, rather a linear components. So this is the expression then. dq is del q del x of dx plus of del q del p or del delta p of d delta p. Is this much okay?
Ma'am, here K1 and K2 are constants.
Now the thing is that this del q del x, because what is the, as I told you in the previous class itself, yesterday's class, that how much are you thinking large movements of x and y?
No, ma'am.
Is this delta q or is it dq? It is dq. So these are small movements, small increments, small changes. Okay. So since these are small changes, hence this partial derivative, this can be considered to be a constant. Even if it's not a constant, does not matter. K1 could have a profile of itself. But you're denoting this one as a K1 parameter. This is the parameter associated with the dx. And this is the parameter minus K2 associated with this one. Now, why is this positive and this one negative? Because of the nature of the changes. If this one shifts to the right, this also shifts to the right. Y also shifts to the right. So, there's oil flowing into this one. Oil flow rate is positive into this one. Okay. While this one is negatively impacted by change in delta P. So, hence this is minus K2. Oil flow rate will be balanced by the pressure differential. Okay, so this pressure differential will try to restore it so that this oil flow rate goes down to zero. It's a restorative function. Okay, so hence this is negatively impacted. So hence this is minus K2. For our purpose here, since we are considering small changes, so here we are considering at the first set that it's constant. K1 and K2 are constants. If you want to do a even higher order modeling or something, if you want to build in other dynamics into it, you are free to do that. That can be done. Okay?
Yes, ma'am.
Yeah. Now about the dither part. Now, this dithering part actually is related to instrumentation basics. So, in instrumentation, the objective is to control this system. And in order to control a system, just think about the basic friction concepts. So, if you're thinking about friction concept, when is it easier to move a body from rest or while it is in motion?
While in motion.
Right. So, while in motion. So now, while in what is the difference in these two? What is the parametric difference in these two? In terms of friction, when you are trying to move it from static friction is there, while when you are trying to move it in motion, so that is dynamic friction. And dynamic friction is lesser than static. Okay, so the system response or the system sensitivity to any kind of input is much better when it is already in some dynamics. Right? Yes, no's?
Yes, ma'am.
Yes, ma'am.
Yeah. So what happens is, so in order to retain that, so what we do is that on this pilot valve, see, this pilot valve could have been like in normal conditions, what would you think of? That it would be steady, just at a stop. Only when you wanted this one to move, would you put in some input into this one. But that would be like moving this pilot valve in this oily environment, fluid environment, but it would be moving it from static condition. So that would leave much larger energy and also some initial time and some lag would come in the response. Typical RC kind of characteristics would come in. Can you appreciate that? Anindita and the others. Yes, no?
Ma'am, why is the high, it's written high frequency and low amplitudes in
Yeah, I'm coming to that. But
yes, ma'am.
This part, have you understood this part? That we would not like to keep it at rest. Is that okay?
Yes, ma'am.
Okay. So it is not advisable to keep this at rest, because then trying to move it in order to get this to move whenever we need this to move would be much more difficult. So what to do? If we give a high amplitude signal to this one, this will move a large distance. You don't want to do that. So hence what would you do? You would put in a low amplitude signal. Right? Is this much okay now?
Yes, ma'am.
Now, if you give a low amplitude signal, say a DC low amplitude signal, that means a step input. So that means there was no input, and after that it's slowly moving right. But then it will move in one direction itself. But that will cause this one also to move. So you will not get the equilibrium condition at all. But that is not the objective. The objective is to keep this in motion so that it is easier, so that it responds easily to whenever a definite input is given from the control system. So what to do then? Put a sinusoidal input here. So sinusoidal input is called, practically it is called a Dieter signal. What is that? A high frequency. For a mechanical system, anything higher than 5 to 7 hertz or 10 hertz is a high frequency. Okay? So there's a small constant jitter or a dither. It'll just keep on kind of shifting around this one itself. It's a sinusoid. Around that low amplitude sinusoid. Can you understand that now?
Yes, ma'am.
Can you tell me a case in practice? Where have you encountered dither signals? I believe, yeah, all of you would have. All of you have. Not would have.
Screw gauge.
Screw gauge, practically when you are handling by hand, you can't. No, you have experienced dithers. So I'm asking you for your experience of dither.
Engines running in a car.
Yeah, so when the engine is in the stalling mode, like when you are at a signal or something, particularly in a bus at a signal, waiting, the driver has not switched off the engine. So that signal is a typical dither signal.
I'm in the neutral position
Yeah.
when the gear is.
So what happens is that the engine is still running, right? So since the engine is running, so that the motion of that engine itself creates a high frequency signal, and it's a very low amplitude, right? You don't jump on your seats because of the engine being on, do you?
No, ma'am.
But there's a constant movement. There's a constant movement there, right?
Yes, ma'am.
That is nothing but a dither signal. So that the moment the signal is the traffic signal is green, he can just move into gear and get the bus to go. So the bus will respond. So the power piston, that movement piston, which rolls the wheels, okay? So this dither is already there. So once the definite input is now provided using the gear and his steering, so from that part, then, and he releases the brake. So this one now takes over. Okay? That is a hydraulic actuator. Okay?
Yes, ma'am.
Yes, ma'am.
Anandita, clear with you or still any?
Yes, ma'am, clear. Ma'am, could you please explain the concept of non-touching loops?
Non-touching. Could you guide me to which page it's on? 8 or 9, huh? Or you just want the concept? Yeah. Okay, let me think of this one itself. Right? So the two inputs here, let me just take up this particular itself. So R1 and R2 are the two inputs and the outputs X1 and X2. So individual loop gains. Now we are looking at loop gains. So loop gains, what are the loops? So this is one loop, this is another loop, and this is another loop, right? Okay. Is this much must be okay.
Yes, ma'am.
Yeah. Now, and the next stage, actually this non-touching loop came in because this one, it started from here. Sum of gain products of all possible, sum of all gains, then that means all loops, loop gains. sum of gain product of all possible combinations of 2 non-touching loops, then 3 non-touching loops, and so on and so forth. It goes on that way, right? So this is where that non-touching loop concept came in. Now, so the non-touching means, so there are 3 loops here with these 3 loop gains, with the respective loop gains being this, this, and that. Okay? Give me yeses or no's.
Yes, ma'am.
Yeah. So now let us look at combinations. If we look at this combination A1 and A22, that means it is this loop and it is this loop. Are they touching each other? Is there any node which is shared between them?
No, ma'am.
Okay, so these are not touching. What about the other, any other combination? Other combinations could be this and this and this and this. Are these not touching?
No, ma'am. They are sharing a node.
Right. So that's a simple concept. When you go on to 3 non-touching, supposing I had to test for 3 non-touching, what would I do, Anindita?
Ma'am, then there needs to be another loop which is not sharing any nodes with the first loop.
Sorry, just a minute. Just a minute. সোমালি ক্লাস চলছে আমি ক্লাসের পরে তোমাকে আমি ফোন করব একবার হ্যাঁ তবে ছবিগুলো দেখতে পাচ্ছি না ওকে so yeah the simplest way of going about it sorry I didn't get your I kind of got part of your answer I'm answering it myself so the simplest way of going about this is 2 non-touching loops already you know now take this combination and compare it with any of the remaining ones. So since this is already a combination, obviously you can't, no point comparing with this and this. These are part of this non-touching loop system, right?
Yes, ma'am.
So if you compare it with this one now, that's the only other option left. So that would give you 3 loops, this, this and this, with these 2 being already non-touching. But this and this, whatever combination you take, there are common nodes. So there are no 3 non-touching loop combinations.
Yes, ma'am. So there necessarily needs to be another loop which is not sharing any nodes with the first two.
Yes. In case you had the 3 non-touching loops, supposing you had one of that, what would you do? Again, you would take that combination because that is already 3 non-touching and compare it with any of the left out others. And check
Yes,
whether you have any 4 non-touching or not.
Yes, ma'am. Yes.
Okay. So that is how you would go about it. Yeah, I think I did not explain it. Did not need to or did not explain it. Nobody asked. Okay. What else?
Ma'am, in the like example that you did where there was a very complex block diagram and you simplified it using operations, ma'am, I had doubt in that question.
Which just tell me the slide number. That's easier.
Like 2 slides ago, I guess. One more, ma'am.
This one.
Yes, ma'am. So basically, we can shift the, ma'am, there are 3 x's, right, ma'am? We can shift the first x to the second x to the first x and the third x to the last, ma'am, that I got. But there are 2 loops between these. How do we connect those 2 loops?
Wait. X's meaning?
Like somewhat, ma'am.
Yeah, summing points. Okay. Yeah. Comparators or summers. Yeah. Okay. So please do not say X's. That's so wrong a thing to say. Yeah.
So we can shift these, then we get R2C1S, ma'am, that I got, ma'am. But
now, okay, Shuddha Shatu, let me kind of this before we get into. I'll come back to you again with your query, but before we get into that, let me point out some more things. Please understand that the way I have resolved this one here is just one way of going about it. There are several possible ways. What is another way? I could have shifted this, like in this, for this configuration, what I did was, we shifted this one out here to before this block, okay? And this was moved after the block. This branch point was moved after the block, right?
yes, ma'am.
Okay, and that we use the properties, this ahead of block, behind block, and pick off point. We use these properties, basic properties. Okay, Now, sorry. Now, instead of doing that, I could actually have shifted this one here also. But then what would have happened is I would still need one more operation because this is a summer and this is a branch off. And again, if I shifted this one also here, this would again be another summer and another branch off. So I would need another operation to shift it before this one, and then because it's a summer, so this would necessarily branch off would have to appear on this branch as well as on this branch, and so on and so forth. Anybody who does that is not wrong. Please understand that. It's not wrong, provided you use the properties properly and systematically. Okay, but since this is also a summer and this is a summer, so moving it here, and there are three entities here, so moving it here just took up three of these. There was already the signal coming in, this also. So since you're moving it to before this, so naturally this gets multiplied by the inverse of this one. Okay, and then because you're shifting this one, this also same logic. This is a pick-off point, this is also a pick-off point. So it can be another pick-off point from this point itself. So three pick-offs rather from at this node. So it simplifies matters. So this is why this was moved ahead the block and this was moved after the block. Okay. Now, next question you asked was something about these two. Where did I get these two and what happened? Something like that?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Okay. Now, so if you shifted this one out here, think of this diagram. If you already shifted this one here, so I have not drawn out this part because this was my rough work in class, or maybe in the lecture also I should have drawn it out. I think I would have drawn it out.
Yes, ma'am. You did.
So if this one has shifted out here, what has happened here? This has become one feedback loop, unity feedback loop. And this has shifted out here. So this has also become another feedback loop. Okay. And because this is a pick-off point on a pick-off point, so I can consider that whether I can consider this as a common pick-off point with three pick-offs, or else I could have shifted, I can shift this pick-off point beyond this point also, does not matter. It's a pick-off point. So a pick-off point is a pick-off point. Before or after will not matter. Similarly, a summing junction, it's a common summing junction. I can again break it up into two summing junctions. And now I could place this one with this one ahead, and then I can take another one with this one coming in after. So this will be an independent unity feedback loop. This will also be another independent feedback loop. With this one going after this point, and this one effectively, you can shift it now before this point also. Is this clear?
Yes, ma'am. I got it now, ma'am.
Because they are the same entities. Because they are the same entities. Otherwise, you can't. Like as I said, like had you been shifting this one here and this one here, then because it would be a mix of summing and pick-off, so you would have to be careful about if you are trying to move this before the summing. So you would again have to take care of the property. But in this case, because it's summer and summer, so which sum you are doing ahead, you can break it up into two components. So which sum you do ahead is immaterial. It's a linear system. So superposition being valid, you can always do that, this or that, earlier or later. Okay. So once you've got that, so this is an independent, this one, I think you got this one, and once you understand that there's an independent feedback loop, so I think this and this are clear now.
Yes, ma'am. Yes.
Right? And then this is another feedback loop, a general feedback loop, not unity, but general feedback loop. Though it's going from above, but it's actually a feedback, negative feedback at that. So then you simplify it. G by 1 plus of GH of S. And G is obviously this one. This is the H. Yeah. Anything else? Or anybody has any further query on this?
Ma'am, the last 2 pages of this PDF, ma'am, were not covered in lecture 5, ma'am, will you be accepting doubts about that next class? Last 3 pages.
Last three signal flows.
Yes, ma'am.
See, understand one thing, that since this is in the we are doing this in the sort of the flipped classroom mode, okay, and it is not as if I have not made the videos available to you. Do you have a problem accessing the videos?
No, ma'am.
You don't. Do you have the PDF supporting? You have the total PDF as to the content,
Yes, ma'am.
right? So you can surely go ahead and do that one up. Have I told
Yes,
you
ma'am. Yes,
that
ma'am.
videos, please look into videos, this and that? I have told you to look into LCS 3 and 4, the note material, and look up the corresponding video lectures. Isn't that so?
Yes, ma'am. Yes.
Yeah. So, and frankly, this material, since you are doing it online and you have the scope of doing it up, so why don't you make use of the time in taking it up from the next lecture? Why keep it for the next? In a class, a situation is different. But if you're making use of this, so it is better that it's easier to follow that. See, if I was taking a normal offline class or even an online lecture fully, I would have been dealing with it differently. I would have to keep note of where I stopped and so on and so forth. But in this, it's easier for me to keep that and okay, this lecture note is done till this point. Otherwise, I can't progress further. It's not, see, at any point of time, if you come up with queries regarding any of the notes, previous notes, I will surely address that. As a teacher, I think I'm morally bound to, and even as a teacher, even otherwise, apart from that moral binding and so on and so forth, I would automatically do it. I'll never say no at any point. But you could and you should, at least from your part, do put in that much of an effort of listening in into a video lecture. One or one and a half or two video lectures. Not that difficult. I'm giving you the material in advance for a week, right? You have time. It's
Yes,
not that
ma'am.
you don't have time. Of course, while I'm saying this, I'm also aware that out of the right now there are about 20, 21 of you or so. Yeah, so 21 of you there. Because two are mine as a meeting host and as a presenter. So there are 21 of you. And out of the 21 of you, my judgment would be that at max 10, 5 to 10 of you would have actually looked into the video lectures, bothered to have. Am I wrong? Obirup, have you? Let me know.
Ma'am, I have gone through the first and second one, and I'm still, matlab, I have started LCS. I haven't like completed third and fourth yet.
Okay, but we are completing of LCS 4. We were supposed to
Yes, ma'am.
complete up LCS 4 today.
Yes, ma'am. I have slowed down a bit right now.
Any particular reason?
Ma'am, I was concentrating on analog electronics 1 and 2. I was finishing the previous semester's analog electronics.
Oh, so this also you go in binge mode, is it? The moment it's a lecture, the videos available.
Yes, sir.
Okay. Anindita, I think you're up to par, or for you also it's the same thing as Shuddha Shatru. You are also
Ma'am, which one? The fifth lecture, half of it I could complete. The other half I
then
haven't.
half of it would have covered up to this 10th thing, isn't it?
Yes, ma'am. Not this page. The previous one. The non-touching loops part. That. Yes, ma'am. Yes, ma'am. Yes, ma'am.
Oh, this is still left.
Yes, ma'am.
Oh, acha. Ankit, what about you?
Ma'am, I am a
By
few.
the way, is there any particular thing? I forgot that Sangram is recording this one. I don't think I need you sort of these things recorded that way. So, do you need anything more recorded from this thing? Any other particular query on this one? Let's first answer that. Then I'll come
Ma'am,
in.
I have,
Huh?
ma'am, I have one query.
Yeah, sure, Gulshan.
Ma'am, in the multivariable system, that page.
This one, right?
Yes, ma'am. Ma'am, here the inputs are uh, V, W, and D are column vectors.
Yes.
And ma'am, this R, V, W, D column.
No. Actually, yeah, they can be column vectors. Yeah, column vectors. In general, column vectors. I was
Yes,
talking
ma'am.
about
So,
multi-dimensional.
ma'am, where you have written the expression for C equals to G1, G12, G13, G14 times the column vector of R, W, R, V, W, and D. So this
Yes.
is a column vector of column vectors.
Yeah. See, the thing is, I hope you got these dimensions. How we were getting these
Yes, ma'am.
dimensions.
Yes,
I
ma'am.
hope you
That is
got
okay.
that
Yes,
one,
ma'am.
right?
That
Okay.
is okay. Yes, ma'am.
So once you have got these dimensions, after that, are you okay with this expression?
Yes, ma'am. Only that expression only what I'm saying is, ma'am, here G11 and
Okay,
G12.
no, that's all right. But are you okay that how could I write this one? Are you okay with that?
Yes, ma'am. We could write it, but ma'am, I have doubt in that part only.
Yes, I'm further elucidating. So technically speaking, like you appreciate that okay, since this is the system, so G11, G12, G13, G14, this would be the transfer functions of the system, and these would be the four inputs, and you would have the overall C, which is coming at us that. Okay, these are the transfer functions corresponding to R, corresponding to V, corresponding to W, corresponding to D. Okay, so
Um,
supposing that, like, how are you finding this one? Now look at this one. So when you say G11, how are you finding this one? This one, considering the all of the rest are zero.
Ma'am, that part is okay. Ma'am, what I'm
Yeah.
saying is,
So
this G11,
what I'm saying is, now look at this. So what is G11? G11 is essentially G1 G2 by 1 plus of G1 G2 H1 H2. This much is okay.
yes, ma'am.
Now what is the dimension of G11 then? Dimension of G11 will be dimension of G1 into dimension of G2. M cross R into
Yes, ma'am.
G2 into G1. Actually, if I should have correctly written it as G2 into G1, okay, because these are multivariables. So G2 operates on G1. It should have been G2 followed by G1. Otherwise, you won't have this multiple coming in. See, R is
Yes, ma'am. Yes,
followed
ma'am.
by
First G1 will be operating on that, then G2 will be operating.
yes.
Ma'am, what I'm saying is, we have written divided by 1 plus G1, G2, H1, H2. So all these are matrices. So, ma'am, how can we
Oh,
divide it? Like,
yeah,
it should be inverted.
I have kind of used a mixed notation here. Although I was writing, you're absolutely right here. Although I was writing multivariables,
And ma'am, these are like non-square matrices in general. So
yeah.
we wouldn't be even sure if there exist inverses.
Just a minute. You are absolutely right. Let me give you the formal thing. Just a minute. Just allow me to open the program. Yeah. Okay. Let me just kind of scroll down. Just allow me to kind of get to that one. The matrix. Matrix. Yeah. Yeah. I hope you can see this.
Yes, ma'am.
Okay. So it's essentially this system. Right? It's the same system. Okay?
Yes, ma'am.
Now, so if you see this, I should actually have been writing it as this. So C would be this inverse times G2 G1, you know. So what I wrote there as G2 G1 by this, I should
even in this one,
this inverse into G2 G1 times R.
ma'am, how? Yes, ma'am. How would we determine which one would come first, the G1 G2 R matrix, G1 G2 matrix, or one IN plus G2 G1 H2 H1 inverse?
Very simple, very simple. As you did it for the single loop. So see, R minus of F2 is equal to E1. Okay, here R minus of F2 is equal to E1. Then further on, G1 E1 plus of V is equal to E2. Okay, G2 E2 plus of W is equal to C. Right? So those basic relations, they are still valid.
Yes, ma'am.
Okay.
Yes, ma'am.
And just keep on substituting one into the other systematically, keeping their locations right. Now I can't,
Yes,
because it's multivariables, so I should not be writing E1, G1 E1 is not the same as E1 G1.
Yes, ma'am.
Right. So what we have is, you have these relations. E1 is equal to R minus F2, E2 is equal to G1 E1, C is equal to G2 E2, F1 is equal to H1 C, F2 is equal to H2 F1.
Yes, ma'am.
So C, as you see here, C was G2 E2, and in place of E2, what can you write? E2 is G1 E1. So G1 E1 will come in here. C is equal to G2 G1 E1. Okay, and then in F2 again, if you substitute for F1, you will get H2 H1 times C. For C, you will substitute this one again, G2 G1 E1.
Yes, ma'am.
Right? And then for E1, you will again put R minus of F2.
Yes, ma'am.
You already know what it is.
Yes, ma'am. I got it.
Okay.
So, ma'am, if we replace,
C is equal to this whole thing.
yes, ma'am.
Okay, C is equal to this whole thing. Now C is equal to this whole thing means you can again keep this, transfer this term because it is a C at the end. So you can shift it to the left side. So you get I plus of this is equal to C. And now look at the order here. The order is very important. G2 operating on G1. So G2 G1. Okay. And this thing now goes in the feedback loop. So it is operated, H2 operated by H1. That is that F2 component coming in. Okay. So this is the particular order that will come in also.
Yes, ma'am.
Okay. And because this is this, so naturally, in order to get C, what will have you do, have to do? You will have to pre-multiply left and right with the inverse of this one. You can't post-multiply. If you post-multiply after C, it will not make any sense. It will not cancel out this one to I. Right? So you'll have to pre-multiply with its inverse. So the moment you do that, you will end up with C is equal to this inverse times G2 G1 times of R. Okay.
So, ma'am, if we want to replace it by a like closed loop diagram, then we will have to first introduce G2 G1 G2 matrix and then this transfer function, the inverse one. Like we'll go from right to left.
Yeah, but you could only reduce it if you consider the other inputs to be 0.
Other inputs to be, yes, ma'am, it's written in terms of R. Yes, ma'am.
Yeah, okay. So between C and R, so R, then this particular block would come in and that would give you C. That would be the reduction. Okay.
So, ma'am, if you do it for all other inputs like VD and W also.
Exactly similarly for all of the others. Actually, in this particular part.
So, ma'am, we can replace that block diagram with the corresponding C and R relations, like
yeah,
individual relations.
See, I'm showing you. Here. This is E1 and E2 related to R and V, and C related to W, and F1 related to D. Okay, so you can have all the combinations. And what you can do further matrix manipulations on this. So all of that is indicated. What I can do is, yeah, so as not to confuse you too much, these particular pages I'll sort of,
Yes, ma'am.
yeah, because you asked, so yeah, see, now this is the whole system. Can you see this?
Yes, ma'am.
These are the G11, G12, G21, sorry, G13 and G14 that are given here. I've very simply written them like this by that, this by that. Okay, absolutely right that it should be matrices, so inverses. So it would be nothing but these actually. And you can work them out just the similar way. Okay, so up to this point, I'll surely give you. In fact, there's a problem worked out here also. This also you should be able to do or appreciate. Yeah, so I'll give you up to this part. I'll take a snapshot of this one and provide it to you as the material. Okay. Right?
Yes, ma'am.
Okay. Now, so actually, you very correctly pointed out that these are actually vectors. Okay. So even you could put in one vector after the other, after the other, after the other. These will be the suitable dimensions. Okay, and you would still be expanding them out like this. That would still be admissible. It is this, considering that the system can be represented as a linear system. That means superposition is valid. Okay.
Yes, ma'am.
Yeah.
Ma'am, I have one more doubt from
Yes.
the that linearization part.
So ahead, right?
Ma'am, yes, ma'am. The second page, I guess.
This one?
Ma'am, above that page.
Yeah. Oh.
Ma'am, the concept of Jordan matrix. Ma'am,
Oh.
where is it coming from? Like where are you using the Jordan matrix in this approximation?
Jordan matrix is, see, oh, okay. So the moment I'm thinking of, say, these parameters, the moment they are coming in, you know, okay. So these parameters, this partial derivatives, these are going to form the
Yes, ma'am.
elements in the Jordan matrix. So if I were to write a dimensional representation, if I were looking at Q dot, and if I were representing it in the standard state space kind of a notation or something, then the corresponding equations, if apart from this one, you can represent this one also, but a set of equations or whatever, so that would form a Jordan matrix. You want to see a Jordan matrix? Let me give a search here.
And so the linear approximation is done using Jordan matrix here.
No.
Like,
the linear approximation leads to a Jordan matrix. That was what I was indicating.
so that would be for a vector valued function.
These partial derivatives, what happens is that, see, you have got a non-linear relation here, right? Y is equal to f of
Yes.
x1, x2, whatever. You can extend it to n number of variables. So that you have a non-linear relation, just as you had
Yes, ma'am.
here. Now, what did you do? Did you keep it the non-linear? No, you did not. You
Linear.
tended to transfer it because all the like the analytical framework is there in the linear systems. A lot of it is available here. So we linearized it, right? How did we linearize
Yes,
it? By taking partial derivatives, right? So how do you take partial derivatives? You use this same concept, Taylor series expansion. This is for one dimensional. You can extend it to two dimensionals, n dimensions also. Okay.
Yes,
No?
ma'am.
Now, so when you
Ma'am.
extend, yeah.
Ma'am, what I'm saying is like, ma'am, I have learned in multivariable calculus that if the function is scalar valued, then you use the gradient to approximate the linear if you want the linear
What is a
approximation.
gradient? What
And
is a
Hessian,
gradient? What is the
ma'am,
mathematical
gradient would
form
be,
of a gradient? How do you calculate a
ma'am,
gradient?
it's not a with the partial derivatives.
Yeah. So these are the partial derivatives, aren't they?
I remember it is not a matrix, and Jordan, as you're saying, is a matrix.
No, it's a Jordan matrix. See, you've got a set of equations, you will get a Jordan matrix. I'll show you in a little bit. So first get to this part. So you are, in order to linearize, what are you doing? You are expanding about Taylor series expansion. So you expand about some equilibrium value, this equilibrium
ma'am.
value x0, y0. Okay. So if there are further dimensions on the x's, so x1, 0, 2, x2, 0, so that would be two dimensions x1 and x2, and with respect to that you would be looking at a y0, y direction. Okay, so then these would be your partial derivatives, and these would be linearized terms, right?
Yes.
As I showed in the next one, and as Shuddha Shakta also queried, that madam, do they have to be constants? They could be constants, they could be further functions also.
Yes, ma'am.
But if we treat them as constants, so the Jordanian matrix, again, the elements you would expect them to be constants. In case they are not, you can take it down to another round of expansion, okay, and you would get the Hessian. Hessian is the second order derivatives.
Second order, yes, ma'am.
Okay. Now, so once you have a set of equations like that, y1, y2, y3, y4, so on and so forth, for x1 to xn, disregard this part. Then what would happen?
Yes,
You would
ma'am.
get these del f's and this one, these sequences of del f1, del x1, del f1, del x2, del f1, del xn. Then you would get del f2, del x1 to del xn. Then del f m up for that. Okay. So if you compounded that, so you could write the y1 to ym. This would be a vector, y1 to ym. Okay.
Yes, ma'am.
And the y tilde, if I call it, without this part. So just the varying part. So y tilde 1 to y tilde ym. Okay. Disregarding the second orders. Disregarding, so because it's a tilde, you don't have this one. So what would you land up with? You would have this into this, into this. So these terms would be there. x1 minus x0,
Yes, ma'am.
x2 minus x0, these are all there. So you can think of that as another vector, x1
Yes, ma'am. Yes, ma'am.
tilde, x2 tilde, and so on and so forth, up to xn tilde.
Yes, ma'am.
That will be a vector. So y is a vector, x is a vector. In between, what will be there? This will be the matrix of these partial derivatives. Del f1, del x1. The first row will be del f1, del x1 up to del fn, del xn, del f1, del xn. And this will go down in the first column from del f1, del x1 to del f2 to up to del fn, n, del x1, and so on. It will form that matrix.
Yes, ma'am. Now I got it. Ma'am, it's about like
the Jordan matrix.
if the function is vector valued, then only we are talking about the Jordan matrix.
Yeah, if there are multiple inputs.
Yes, ma'am. Now got it. Got it.
Yeah. Now let me just try and show you. Just a minute. Yeah. Here it's a nonlinear tracking station. Yeah, this is exactly what. Like suppose you've got V1 and you've got an I2 also, right? So this would be a matrix of the two inputs, del I, del V. So this would be the Jordan matrix. Okay.
Yes, ma'am. Got it.
It would still be written somewhere clearly. Yeah, they're getting the Jacobian. Oh, sorry. My bad. I wrote the Jordan matrix. I should have written Jacobian.
And that only. Vector valued functions are linearized by Jacobian matrix.
The Jordan is actually used for the stability part. Jordan is a particular structure. I should correct that off. Yeah. Please correct that off. It's not the Jordan matrix. The Hessian matrix I've written, right? This is Jacobian matrix. Okay. So this will be this one. So this del y is equal to A del x. So this is the Jacobian matrix. Both starts with the J. I just mixed this one up. Jordan is a particular different form which is used for stability purposes. diagonalized matrix and so on. But even what you were talking actually about the Jacobian matrix itself, which you said was a gradient.
Yes,
one.
ma'am.
This is nothing but the gradient matrix. Okay. There'll be examples also. Maybe actually this chapter might answer several of your queries that you know. Okay, so I'll just look it up. I'll remember to see the Jacobian, some example there. Or else I'll at least give up that much. Yeah, any other thing? Anybody, you or anybody else? Yeah? Anybody? Jacobian. Okay. Anything else? Anybody?
No, ma'am.
Okay. Oh. আচ্ছা, আমি বেরিয়ে গেলাম কি করে? Sorry, I seem to have made a mirror or something. Sorry, I somehow repeated myself. I managed to somehow get out of this mode and something. Yeah. So, any other query? Anybody else? No?
No, ma'am.
Yes, no? Anybody?
No,
Let's
ma'am.
stop the recording. When I ask Sangram to stop the recording. I do have something to ask you beyond that. As I was about to start off with Ankit. Hello.
Yes, ma'am, you can stop the recording.
Oh, sorry, my speakers were off. Yeah, so I was unable to listen to whatever you were saying. Yeah. Anybody has anything else? I'm repeating again. Any other queries? Please repeat whatever you said in the last 1 or 2 minutes.
No, ma'am.
Okay. So should I ask Shangram to then stop the recording?
Yes, ma'am.
Okay. So Shangram, you can stop the recording. Okay.